Hi, everybody. It's Professor Mitchell, and today we're starting applications of definite integrals, starting with volumes using cross sections. In this section, we will calculate volumes of solids by slicing. We'll calculate volumes of solids of revolution using the disks method. And finally, we'll calculate volumes of solids of revolution using the washers method. All right, so the idea is that you have a solid like the one pictured here, and we want to calculate the volume of this solid. So what we're going to do is slice it into cross sections at each point in the interval from A to B. So we'll form a cross section called S of X because the particular cross section will depend on the value of X. And that cross section is formed by intersecting the solid with a plane that is perpendicular to the x-axis through the point X. And that's going to give us a planar region, like one of the blue ones you see here, whose area is A of X. All right, so what we're looking at here is a close-up of the little section that you see right here going from X sub K minus 1 to X sub K. Think of those values as being two X values that are pretty close together within the interval from A to B. All right, so this little piece of the solid, they're calling it a slab, a solid thin slab, is approximated by the cylindrical solid with base S of X sub K. So S of X sub K is a region. It's actually the region that you see right here, having an area of A of X sub K and a height of delta X sub K, which is just the difference between X sub K and X sub K minus 1. And at this point, it's helpful to remind you that the volume of a cylinder with a base area B and height H is equal to B times H. All right. So in this case, the volume of this thin slab is going to have a base A of X and a height of delta X. All right, so we will define the volume of a solid of integrable cross-section area A of X from X equals A to X equals B as the integral of A from A to B, which you see here. So the volume is equal to the integral from A to B of A of X dx. All right, so the steps for calculating the volume of a solid by slicing. First, we will sketch the solid and a typical cross section. Next, we'll find a formula for A of X, which is the area of a typical cross section. We'll find the limits of integration, and then we will integrate A of X to find the volume. So for our first example, a pyramid 3 meters high has a square base that is 3 meters on a side. The cross section of the pyramid perpendicular to the altitude X meters down from the vertex is a square X meters on a side. And I'll show you a picture of this on the next slide. So we want to find the volume of this pyramid. All right, so here's what the picture looks like. So notice that we've placed the pyramid along the x-axis. It is 3 meters high, and typical cross section is a square. So for any value of X between 0 and 3, the cross section at the point X is a square, which is X meters on a side. All right, so we've drawn the sketch. And since the cross section at X is a square X meters on a side, its area is going to be A of X equals X squared. The limits of integration are 0 to 3 because the squares lie on the planes from x equals 0 to x equals 3. And finally, we will integrate to find this volume. So what I'll do when these integrals get even just a little bit more complicated is I will switch over to my tablet and work them out live for you. I thought this one was simple enough. It's just the integral from 0 to 3 of x squared dx by what I call the backwards power rule. The integral or an antiderivative for x squared is x cubed over 3. So we plug in 3, plug in 0, and subtract, and we get that the volume of the pyramid is 9 cubic meters. All right, now I was looking at this and trying to figure out why they were calling it an example. It's not an example in the traditional sense. It's just really an application of this idea that we've been using. This is called Cavalieri's principle. And it says that solids with equal altitudes and identical cross-sectional areas at each height have the same volume. And this follows from our definition of volume because the cross-section area function A of x is going to be the same for both solids. And so is the interval from A to B, as you can see in this picture here. So I like the analogy that I saw in the textbook, which is think of these two things as stacks of coins. So this one, the stack is kind of crooked. This one, it's nice and neat, but they both have the same volume because all of the corresponding cross sections are identical. There it is. I knew I saw it somewhere. All right. All right, so that brings us to solids of revolution. This is going to keep us busy for the rest of this section and also in the next section, I believe. So there are several different methods for finding solids of revolution. And first of all, what I mean by a solid of revolution is imagine that you have a curve, let's say sitting over top of the x-axis, and you then revolve that curve. You might be able to picture it here. So this looks like a piece of a circle, and you see this arrow going around the x-axis. We're going to revolve this semicircle, let's say, around the x-axis, and what we're going to end up with will be part of a sphere. All right, so this is a specific kind of solid. It is a solid that is generated by revolving a curve about really any straight line. Usually it will be either the x-axis, the y-axis, or some other horizontal or vertical line. All right. And while we're here, I'll explain this formula to you. So this is an image that I found on Google. So thanks to whoever created this. All right. So we have this curve here, and I'm going to call this curve R of X, R for radius. If you revolve this curve around the x-axis, the thin solid that would be generated by this rectangle would be like it would be a flat disk. That's why this is called the disk method. The volume of that disk is going to be, again, the base times the height, and this time the base will be a circle, and it will be a circle whose radius is R of X. All right, so that's how they get this formula. It's using the previous formula that we talked about, the integral from A to B of A of X. But in this case, because the cross section is a circle, we would use the formula for the area of a circle, and A of X would be pi times R of X, because remember, the area of a circle is pi times R squared. All right, so this is how you find the volume of a solid of revolution using the disk method. When we get to the next method, which is called the washer method, I will explain the difference between the two and how do you know when to use discs and how do you know when to use washers. For the moment, you use discs because that's the only method we know. All right. Okay. So again, here is the formula. So it's the integral from a to b of pi times r of x squared. All right, our first example, the region between the curve y equals the square root of x between 0 and 4, and the x-axis is revolved about the x-axis to generate a solid, and we want to find the volume of this solid. So the first step is we're going to sketch that region, and the region looks like this. So now imagine revolving this region about the x-axis. What you end up with, it's been quite a while since I've taught Calc 3. In Calc 3, we do a lot of stuff with solids. I believe this shape is called a paraboloid. Imagine like a three-dimensional parabola. But that's the solid that you end up with when you revolve this region about the x-axis. Okay, so the distance or the length of this line segment from the x-axis to the curve is r of x, which is the square root of x. So the volume of this solid will be given by this integral, the integral from 0 to 4 of pi times the square of the square root of x, which of course is just x. And again, this integral is pretty simple. The integral of x, or an antiderivative for x, is x squared over 2. So we plug in 4, plug in 0, and then find the difference. We end up with pi times 4 squared over 2, which comes out to 8 pi. All right, so in the next example, we'll find the volume of the solid generated by revolving the region bounded by y equals the square root of x and the lines y equals 1 and x equals 4 about the line y equals 1. So here's an example where the axis of revolution is not the x-axis. Those generally take a little bit more thought. In fact, let me switch over to the tablet right now so you can see some more explanation of what you're looking at here. All right, let me just add a couple more things to this picture. So we're going up to x equals 4. So the region ends here. And we are revolving about the line y equals 1. Okay, so this red line segment represents r of x. So I need to write an expression for r of x. And to get that expression, I am going to note that the distance from, well, let's start here. From here to here is 1. And the distance from here to here is y, which is the square root of x. Right? Because this curve is y equals the square root of x. That means the length of the red line segment is just the difference between those two lengths, which would be the square root of x subtract 1. All right, and you can see what that solid looks like. So having drawn those sketches, the volume of this solid is going to be given by the integral from 1 to 4 of pi times r of x squared, where, as we just noted, r of x is the square root of x subtract 1. So multiplying out the square of the square root of x subtract 1, we get x minus 2 square root of x plus 1. Integrating that expression, we get x squared over 2 minus 2 times 2/3 x to the 3 halves plus x. And then plugging in 4, plugging in 1, and subtracting, we end up with 7 pi over 6. So I would encourage you definitely to try this one yourself and make sure that you get 7 pi over 6. I believe starting with the next example, I am going to do these integrals live for you. All right, in this next example, we'll find the volume of a solid of revolution that is generated by revolving about the y-axis. So same formula. This time the limits of integration c to d are y values, and the function has to be written x equals a function of y. For example, find the volume of the solid generated by revolving the region between the parabola x equals y squared plus 1 and the line x equals 3 about the line x equals 3. So here is the picture of that region. And what I recommend doing, in fact, let me just switch over to my tablet. It's easier for me to scribble on it. So the main thing that indicates that this integral is going to be written in terms of y is the fact that when I draw what I call my representative rectangle, which looks like this, for generating the disk, that rectangle is horizontal. Its width is delta y, the change in y. Okay. So what I want to talk about now is what would be the expression for r of y. Remember that the equation for this parabola is x equals y squared plus 1. So that is the length of the line segment going from the y-axis to the parabola. No, I'm sorry. What I said was correct. What I was starting to write, though, was in the wrong place. This distance here is y squared plus 1. That is the distance from the y-axis to the parabola. This longer distance from the y-axis to the line x equals 3, that distance is 3. Okay. So the red line segment, its length is r of y, and that would simply be the difference between 3 and y squared plus 1, which comes out to 2 minus y squared. So the last thing that we need before we set up our integral is the limits of integration. The limits of integration, again, are going to be y values that are going to be determined by these 2 points, because that's where the region starts and stops as you move from bottom to top. Those are the points where x equals y squared plus 1 and x equals 3 intersect. So that would be where y squared plus 1 is equal to 3. And of course, that means where y squared is equal to 2, which means y is the positive or negative square root of 2. So those are going to be our limits of integration. All right, so this is our integral. It goes from negative root 2 to root 2, pi times the square of 2 minus y squared. Remember, 2 minus y squared is r of y. So I will go ahead and evaluate this one for you live. Multiplying out the square of 2 minus y squared, we get 4 minus 4y squared plus y to the fourth. And then using the backwards power rule to get the antiderivative, that would be 4y minus 4y cubed over 3 plus y to the fifth over 5. We're going to plug in root 2 and then plug in negative root 2. So that'll be 4 root 2 minus 4 times root 2 cubed over 3 plus root 2 to the fifth over 5. And now I have to subtract the value of that expression at negative root 2. Remember to put it in parentheses. So that'll be negative 4 root 2. We have a minus there, which is going to become a, oh, let's just do it like this. Minus 4 times negative root 2 cubed over 3 plus negative root 2 to the fifth over 5. Okay, so it's a little messy. We have 4 root 2. Okay, now let's go up here just to get some stuff out of the way. Root 2 cubed would be, there we go. Root 2 times root 2 times root 2. So 2 of those will get together and become a 2. So that'll be 2 root 2. And then root 2 to the fifth would just be root 2 cubed, which is 2 root 2, times root 2 squared, which is 2. So that will be, let me open this up a little bit, darn it. 2 root 2 times 2. So that'll be 4 root 2. Okay. So we have 4 times 2 root 2 over 3 plus 4 root 2 over 5 plus, so now I'm distributing the minus sign, 4 root 2. Okay, now this is going, so this is going to be a triple negative. We've got the minus here, the minus here, and the minus in here. So that's going to stay minus. And that's going to be another 4 times root 2. 4 times 2 root 2 over 3. And this will be minus, actually it'll be plus because we have the minus here and we have the minus here. So that'll be plus 4 root 2 over 5. Okay, so now we have some fractions to get together. And let's see if we can knock this out in a little bit of space I have left. If I can write this far down, that's sometimes my challenge. So I have a 4 root 2 and a 4 root 2. Becomes 8 root 2. This is an 8 root 2 over 3. This is another 8 root 2 over 3. So that'll be minus 16 root 2 over 3. I'm going to leave a space next to that because I need to get a common denominator there. And then putting these two together gives me 8 root 2 over 5. So the common denominator will be 15. I'll multiply this by 5 over 5. I'll do this by 3 over 3. And I'll do this by 15 over 15. I don't think I can write that far down. Okay, so we have, this is going to be all over 15. 120 root 2 minus 80 root 2, which is 40 root 2, plus 24 root 2 will give me 64 root 2. So it's going to be 64 root 2 times pi all over 15. Wasn't that fun? That brings us to our last objective for this section, which is the washer method. So now I'll explain the difference between the disk method and the washer method. When you use disks, the region that is being revolved about some line is going to lie flat up against that line, which you can see in this picture is not happening. There's a space between the region and the axis of revolution. So in this case, this region gives you a solid that looks kind of like this. See, it has a big hole in the middle. And the cross section that's generated by the little rectangle looks kind of like a washer, you know, a washer that you put with a bolt or something. So let me switch over to my tablet. I have drawn a picture of that washer so you can understand the formula that we use. So if we call the outer radius of this washer big R of X and the inner radius little r of X, the area of this washer is just the difference between two circles. So it would be the big circle minus the little circle. And this looks an awful lot like what we're going to be using for our formula. The only difference is that the pi will typically be factored out. So that brings us to our formula for finding volume of a solid of revolution using the washer method. This is for rotation about the x-axis. It looks like this: the integral from a to b of pi times the square of big R of X minus the square of little r of X. So our first example for the washer method, the region bounded by the parabola y equals x squared and the line y equals 2x in the first quadrant is revolved about the y-axis to generate a solid. Find the volume of the solid. So for this, I think I'm going to switch over to the tablet. They have a better picture of this region on the slide, and I'll show that to you too. Okay, so what I want to emphasize about this example is because we are revolving the region about the y-axis, that means that the little rectangle, which you see right here, is horizontal, which means that we have to express our integral in terms of y. Okay, so this happens sometimes. So instead of thinking of the parabola as y equals x squared, I'm going to solve it for x, and it's going to become x equals the square root of y. the line y equals 2x. I'm going to solve that for x, and that's going to become x equals y over 2. So the outer radius, big R of y, is going to be the square root of y, and the inner radius, little r of y, is going to be y over 2. And the limits of integration will be 0. Remember, these are y values, up to the point of intersection of these two curves. And it's easiest to get that just by setting x squared equal to 2x, I think. So if you set x squared equal to 2x, that means x squared minus 2x is equal to 0. Factor out the x. You get x times x minus 2 equals 0. And that equation has two solutions, x equals 0 and x equals 2, which means that this point has an x coordinate of 2, but I really need to know the y coordinate. By substituting that into either one of the equations, I get that the y coordinate is 4. So the upper limit of integration will be 4. And we'll switch back to the slides. All right, so there's a better picture of the region that we're going to be revolving about the y-axis. And here is the solid. It's kind of like a bowl with a parabola-shaped outside and a cone-shaped inside. All right, so we have sketched that region, and now our integral looks like this. So I'm going to work that one out for you live. All right, this one shouldn't be too bad. So first we'll square our big R of y and our little r of y, and that's going to give us y minus y squared over 4. Okay, so antiderivative for y is y squared over 2. Antiderivative for y squared over 4 would be 1/4 times y cubed over 3. So that would be y cubed over 12. Plug in 4, plug in 0. And that's going to give us 4 squared is 16. 16 over 2 is 8. 4 cubed is 64. 64 over 12. We can simplify that. And then I'm just going to put over here, substituting 0 into both of those gives you 0. 64 and 12 have a common factor 4. So that's going to reduce to 16 over 3. And then multiplying 8 by 3 over 3. All right, we get pi times 24 over 3 minus over 3 minus 16 over 3, which is 8 pi over 3. All right, and that's going to do it for this section. We'll see you next time.